I'm Reverend Greg, and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. This time we'll look into brightness, contrast and saturation. As always, a short disclaimer. This tutorial is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistakes in my video or see any better way to solve a problem, please add a comment so everyone can learn from you. We already established some important concepts in the video about the first simple shaders, so I'm going to up the pace a little bit and there's a few things I won't explain anymore. I'm not going to explain float and vector data types, or how to construct a vector from floats and how to add, subtract, multiply or divide component-wise. I'm not going to explain what VV color is and how to set up a uniform float. This video won't teach new things about GLSL. This and the next few videos are about how to create an effect you want by just using the simple GLS elements we already learned and about reading shader code written for other engines. This is a shader I created. I wanted to create some gritty contrast effect and I realized I'll need to look into brightness, contrast and saturation, and that's what we're going to do together now too. That's a lot to cover, so let's start with brightness. Before coding the shader, we need to understand what brightness is. This is the curve's adjustment of GIMP. On the x-axis is the color as it appears in the original image. x0 is black and x1 is white. On the y-axis is the color output after applying the adjustment. y0 again is black and y1 is white. The linear 45-degree line in the graph just shows that at the moment output is equal to input. To increase brightness, we just parallel shift the output. If we shift it upwards, everything gets brighter and will eventually become white. And if we shift down, everything gets darker and will eventually become black. So brightness is easy to understand. The luminance of a color is more or less defined by the sum of its R, G and B components. If all channels are 0 or less, the color is black, and if all are 1 or more, the color is white. This means if we add 1 to each channel, every pixel will be white, and if we subtract 1, every pixel will be black. I'm creating a new shader and call it shader brightness. Close the vertex shader. I'll also copy my base module and rename it. Then place it in the test room. And set up the usual basic stuff like info text, sprite and shader. I'll use a uniform and I'm going to call the handler uBrightness and the uniform brightness. In draw event I'm creating a local variable brightness and set it to global.slider1 times 2 minus 1. Since my base project global slider 1 times 2 minus 1 will return a range from -1 to 1, then I pass that to the uniform brightness of the shader. If you're not using my base project, just create a timer going from -1 to +1 and back, or simply set a constant within that range. I'll also add a simple helper from the base project. Script draw corner info overlays the upper left corner of the module with a small info box. And all I want to show is the variable brightness, so the text I pass into the script is b plus string brightness. So all we need to do inside the fragment shader is adding the uniform brightness to all color channels, and since we set up the uniform to range from -1 to 1, this means the colors will go from black to white. So I'll split the pass-through line into 2 once again. Add brightness to the RGB components. and add the uniform float brightness. And that's it already. So let's run the program. And it works. Moving the slider D and increases the brightness to black and white. Now let's compare that to gamma. Many of you probably know the term gamma correction from some game video options. It's that setting where games ask you to adjust brightness so you can just so see a dark logo on a black background. Since each display is different, game developers use gamma correction to let the player see as much as the game designers intended. Darks should stay dark, but not so much that the player can't see important things anymore. So gamma correction adjusts brightness, but in a very different way than a brightness slider we just created a minute ago. I can't tell you the details because I only understand the very basics. Wikipedia is your friend if you really want to know more than I'm explaining in this video. But I can demonstrate about what it does by showing the GIMP curves adjustment again. Changing the gamma level changes that linear input to output line to an exponential curve. If we increase gamma, the curve bends upward and thus increases the overall brightness of the image. But you'll notice that the very dark and very light colors are affected less than the midtones. And if we decrease gamma, the curve bends downward and the overall brightness is decreased as well, again mainly affecting the midtones. The formula used is color to the power of 1 divided by gamma. So gamma 1 will not change the color because power of 1 won't do anything. Gamma lower than 1 will decrease the color value, and gamma higher than 1 will increase the value. So let's code this. First I'll create a shader and name it shader gamma, and close the vertex shader. Then I'll duplicate the template module and name it object gamma. I'll once again set up the standard stuff. Info text, sprite, shader. And now I want a uniform to control the gamma level, and I'll call the handler uGamma and the uniform gamma. In draw event I'll create a local var gamma and set it to global.slider times 2. If you're not using the base project, set it to a tween of your own ranging from 0 to 2, or just set a constant in that range. Then I pass the uniform to the shader. And in the end again I use script draw corner info to show the current gamma level overlaying the sprite. G gamma. In the fragment shader we need to set up the uniform float gamma. Then I'll split the GLFrag color line again and add the gamma adjustment to the RGB. basecall.rgb equals power basecall.rgb vec3 1 divided by gamma. We need to build a vec3 there because the function power is working component-wise and it expects both arguments to be of the same data type. Setting glfrag color to basecall now should be all we need to do. Now I just need to put the object into our test room and run the program. You see that gamma is also affecting brightness, but in a different way. The main difference is that it's also affecting contrast, and the second, that it's not reaching pure white. Let's just set the uniform to be able to reach gamma 10 and see what happens now. And it's still not getting to all white. So that's gamma, and now on to contrast. Increasing contrast means making darks darker and lights lighter. And decreasing contrast means making darks lighter and lights darker. To show what I mean, we'll have a look at the curve adjustments in GIMP once again. We're back at the linear input to output. When we make darks darker and lights lighter, the contrast increases. You'll quickly notice that saturation increases as well. This fact will be important to remember when we get to my gritty contrast shader. And when we make darks lighter and lights darker, we decrease contrast. With no contrast at all, we're left with all pixels being the same grey color. So we need to find a way to push those values away from each other, and the farther away from the middle grey they are, the farther they should be pushed. The easiest way to do that, I think, is like this. Color equals color minus 0.5 to move the middle value to 0, times contrast to stretch the values apart, and plus 0.5 to move the middle value back to the center. So let's start coding. First I create a shader and name it shader contrast, and close the vertex shader. Then I duplicate the base model once more and name the copy object contrast. As usual, I add the standard stuff like info text, sprite, and shader. I already know I want to use a uniform, and I call the handler uContrast and uniform contrast. In draw event, I add a local var contrast and set it to global.slider2 this time, times 5. If you're not using the base project, just create a tween going from 0 to at least 2 and to maximum 5. More doesn't make sense. Then I'll pass the uniform contrast to the shader. And again add the script draw corner info and set its text to C contrast. I'm quickly going to place the object in the test room. Now on to the fragment shader. Here we need to define the uniform float contrast. Then I'll split the glfrag color line again, set glfrag color to base color, and set the base color.rgb to base color.rgb minus 0.5 times contrast plus 0.5. Now let's run the program. Since we set the slider ranging from 0 to 5, contrast 1 will be at slider position 0.2. If we reduce the contrast from there, everything becomes mid-tone grey. If we move the slider to the right, the contrast increases, and as we observed in GIMP, so does the saturation, a side effect of contrasting. But that's contrast, and now we'll look into saturation. First, let's have a quick look at saturation in GIMP. I can't just use the curves to recreate saturation, so I'll use the saturation slider. And we can quickly observe what's happening. Every pixel sort of keeps its value but gets pushed away from its average grey value. And if you remember the video First Simple Shaders in this tutorial series, we created a desaturation shader which did the opposite. The code looked like this. We had a tween going from 0 to 1. I used the base project slider 1 for that. Then we had several versions inside the fragment shader. In version 2 we created a grayscale version and decreased the color value by multiplying it with 1 minus desaturation strength, and increased the grayscale version by the desaturation strength and added both together. In version 5 we still created a gray value but by using the dot product and an anti-SC conversion, and we mixed the colored pixel with the grayscale pixel by desaturation strength. So I guess we can actually just reverse that effect and create a saturation shader like that. Let's dive into coding this. First, duplicate the desaturation shader and name it shader saturation. If you didn't do the First Simple Shaders tutorial, just create a new shader and you'll get a chance to type in the code later. Close the vertex shader. Then duplicate the desaturation object and name it object saturation. Again, if you didn't do the other tutorial, just create a new object and type the code later when we look into its events. Place the new object inside the test room. Now in Create Event, I quickly changed the info text. Then change the shader to shader saturation, the handler to use saturation, and the uniform to saturation. In Draw Event, add a local var saturation and set it to global.slider3 this time. Then set the uniform to use saturation, saturation. As I did in all modules in this video, I also add the script draw corner info and set its text to as:* plus string saturation. Inside the fragment shader, we can safely delete all comment lines. Then change the uniform to saturation. And now we just reverse the mix values. Value 1 should be the gray value and value 2 the base color. Let's run this code. As you see, we've reversed the effect, but we're not saturating yet. For the next step, I'll need to explain something about the mix function. The graph shows mix 0, 1, mix amount. If mix amount is 0 and the result is the first value, which is 0. If the mix amount is 1, the result is the second value, which is 1. If mix amount is 0.5, the result is a linear interpolation halfway between the first value and the second, and so the result is 0.5. That's what we already learned in the video about the first simple shaders. Now what happens if we set mix amount to 2? The function will just continue to interpolate, so at mix amount 2, the result is 2. And at mix amount -1, the result is -1. And that's what we can use to saturate. We won't even need to change the fragment shader. All we need to do is change the value of the uniform. In Draw Event, I'll just multiply global.slider3 by 5 and run the program again. And now we got ourselves a saturation shader. At this point of creating my own shader, I wanted to know how others do brightness, contrast and saturation, and so I looked into some other shaders. It was quite interesting and educative, so let's look into one in particular together. On the mouaiff WordPress blog by Romain Dura, I found a shader library that tries to simulate Photoshop filters. You can download a library on the blog. I'll post a link in the description of this video. After downloading and looking into the library, it is a bit confusing at first. On top, you see some licensing information. If you're using shaders from this library, you should follow these instructions to be safe. Although, to be honest, I think some of the code is either just common sense or someone else's idea anyways. But since probably some code actually is unique and coded by Romain, you might want to rather be safe than sorry. Beneath that you'll see blocks of comments and of code. Each comment block explaining what the next code block is doing. If you scroll down a bit, you'll find a block about brightness, contrast and saturation. And a SourceForge link to a shader pack by a guy called the GameMaker, who did or did not write the code himself, who knows. Anyways, we will just use that code to analyze how he or she programmed the brightness, contrast and saturation shader. Let's create a new shader and call it Shader Brightness Contrast Saturation TGM for the GameMaker. And close the vertex shader. Then duplicate the template module and name it Object Brightness Contrast Sat TGM. Now in Create Event, I'll again set up the basic stuff like info text, sprite, and shader. This time I know I want 3 uniforms, so I'll set them up here already. U brightness for the uniform brightness, U contrast for the uniform contrast, and U saturation for the uniform saturation. In the draw event, I'm going to set up 3 local vars. Var brightness I set to global.slider1, var contrast to global.slider2, and var saturation to global.slider3. And once again, if you don't use the base project, just create 3 tweens. Then I also need to pass the 3 uniforms, brightness, contrast, and saturation, to the shader. And in the end I'll use the script draw corner info again, but for readability I created text in a local var first. And this time I'm not using the function string, I'm using string format, which formats the size of the string. So I want to show B brightness, C contrast, and S saturation. And I'll pass that local var to the script. Now let's place the object in our test room. And copy the shader code from the library and paste it into our fragment shader. I'll paste it just above the main function for now. Before analyzing the shader code, I set the uniforms, brightness, contrast, and saturation. Now let's look at the code we pasted. It's a function, similar to a script or event in GMS, which is why I pasted it before the main function. In GLSL, we can add functions outside the main function and then call them from inside another function, in example from inside the main function. I mentioned in the introduction video part 1 that every function in GLSL needs a return data type. For the main function that's void, meaning it's returning nothing. And for this contrast, saturation, brightness function, it's a vec3. That's because the return value, con_color, is a vec3. Then after the function name we see a list of arguments, each defined by a data type as well. So this function wants a vec3, some color, and 3 floats for brightness, saturation, and contrast. Then he defines 3 constant floats to change an average luminance of the RGB color channels. However, I played around a bit and I don't see its usefulness really. Maybe he just did it to simulate some Photoshop functionality since that's the goal of his shader library. Then he sets a vec3 luminance coefficient. This is similar to what we did several times now to convert color into grayscale, only he's not using the NTSC conversion we used, but something different. As mentioned before, I don't think anyone needs to stick to the NTSC conversion. What matters is how it looks in the end, so I'll leave it at those values. Now he sets up a vec3 from those average luminance constants I don't really get, and the only place he uses that vector is in the contrast lens, so I'll look at it later. Then the brightness. This looks more like contrast to me. He multiplies the color by the contrast factor, so everything black stays black and doesn't get brighter. You can test that by adding a black spot to the sprite, and you'll see it will stay black no matter how much you crank up the brightness. However, since he's pushing the colors from black up and not from gray mid-tone in both directions, like we did in our contrast shader, the result is brightening the image and it does look appealing. Somehow similar to increasing the gamma level in our gamma shader, but not the same. After that, he's creating a vec3 for intensity. What this line does is what we've done several times before in this series. He's converting color to grayscale. So intensity is the value of the pixel. Then he mixes that grayscale with the brightened color and uses saturation as mix factor. So this is the same as we did in our saturation shader. And in the end he mixes the average luminance vector with the saturated color and uses contrast as mix amount. That is doing the same as our brightness shader, but I think in a really interesting way. The average luminance shader is a VEC3 0.5, 0.5, 0.5, which means the mix function is pushing everything from that value and thus is increasing contrast. What I still don't understand is why he sets up the constants to create that average. I don't get why you want the contrast of the red channel behave different than the contrast of the green or blue channel. Because if you do that, this will tint the image, but maybe that's what he wanted. The only reason I could think of would be if you, for example, set everything to 0.3, then the contrast would push from a value of 0.3. But I don't see why you would want to set different values for different color channels. If anyone knows why he implemented that option, please leave a comment. I'm really curious. I don't think he did it by mistake or did something useless. I just think I can't see the use of it yet. And finally, the contrasted color gets returned. This function actually is GameMaker ready from the box. Nothing needs to be changed inside. All we need to do now is call it from the main function, and so let's do that. As usual, I split the GLFrag color line and set up the base color. And GLFrag color I set to contrast saturation brightness, the function. We need to pass a VEC3 color, that's base color.rgb, and our three uniforms in a specific order: brightness, saturation, contrast. The GLFrag color is a VEC4. We still need to grab the base color's alpha, so let's construct a VEC4 with the alpha. From what I saw in the code, having our sliders going from 0 to 1 will not be enough, so let's multiply them all by 2 and run the program. Let's compare the brightness setting with our brightness and gamma shader. As expected, brightness won't be able to bring dark colors all the way up, so it is more like a contrast setting. But it still looks good. Next, let's compare the contrast setting with our contrast shader. It's a bit difficult to compare since our contrast module is set up to send values from 0 to 5 into the shader, and the same with comparing saturation. So I want to change the slider multiplicator in our object BrtConSat TGM, and I'll just multiply the contrast and saturation slider by 5 instead of 2 and run the program again. First I set both to slider position 0.2, so both contrast and saturation have a value of 1. Now when we compare contrast again, we can see it's the same effect. And when we compare saturation, it's also the same. So this was the first time we implemented shader code created by someone else. And now I think we learned everything we need to create the gritty shader I showed at the beginning of this video, and it's time to move to that. First, let's create a new shader one last time in this video and call it shader gritty. And close the vertex shader. Then create a new object and call it object gritty. Now I want to move everything we created in this video so far into a new room. So I cut those objects from the test room, create a new child of the template room, and call it rm_BRTXXCONXXSAT, and paste the objects there on the main layer. The room name object in the base project will replace the double X's with a vertical line. Object gritty I place in the test room for now and move it over to the new room when I'm done. In object gritty's create event, I again set up the standard stuff: info text, sprite, shader. And I want the controls to be as simple as possible, so I only set 2 uniforms. The handler uContrast with the uniform contrast, and the handler uBrightness with the uniform brightness. In draw event I create two local vars again, var contrast on slider 2 and as before multiplied by 5, and var brightness on slider 1, as we did in the brightness shader, multiplied by 2 but then subtracting 1 to have it go from -1 to 1. Then I set the uniforms. uContrast, contrast, and uBrightness, brightness. And in the end again a local text var. Var text b plus string format brightness 1, 2 plus \n c plus string format contrast 1, 2, and pass that to the script draw corner info. Now to the fragment shader. First set the uniforms, contrast and brightness. Next split the line again. Then set the contrast. base_RGB is base_RGB minus 0.5 times contrast plus 0.5. And the brightness, base_RGB is base_RGB plus brightness. Let's have a look at that for now. Since color values can get below 0 and 1, we're not getting to all black or all white now. One workaround would be to set brightness before contrast. So let's swap that and test. That's quite good already, but I'm not happy with how it feels. So another option. Clamp the contrasted color so no channel can be below 0 or above 1. And let's test that. Depending on what you want, this might be the way to go, but for my gritty shader, it's not. What I wanted was something like with brightness before contrast, but a better feel to it. And because I didn't find an elegant way, I went for a dirty way. I just multiplied brightness by 1 plus contrast times 0.5. This looks right and to me seems to be easier to handle. But to get a gritty look, I need to get rid of the saturation that came from increasing the contrast. First, let's get the grayscale as usual, but after the contrast is applied. Float gray is dot product of base_RGB and the NTSC conversion vector. Then we do the desaturation mix. base_RGB is mix of base_RGB and the grayscale vector. But what will be a mix amount? Now the mix amount needs to depend on the contrast, since I want to negate the saturation increase coming from increasing the contrast. The only solution I came up with was this. Max of contrast minus 1 or 0 times 0.25. At contrast 1 I want no change, so the mix amount has to be 0. At contrast below 1 I want no change either, or the colors would invert, so I have to max the amount to 0. Test it without the max function to see what happens at contrast between 0 and 1 if you want to. At contrast higher than 1, however, I want to start mixing in the gray value. I played around with some factors and for me 0.25 worked fine. So let's run this again. And that's it. That's the gritty shader I made. Now I know this video got rather long, but I think it's interesting to see what brightness, contrast and saturation are, and I think understanding this will help a lot when creating other shaders, like the gritty shader we just created. The next few videos will be about creating some other shaders with the same tools. I hope I can keep those videos shorter, but especially one I got planned, a day and night cycle shader, will probably take some time as well. After those few videos, I'll start to use VB text core, so we'll finally have more tools to use when creating a shader. Until next time.